questions for people here in Victoria. Thank you.
First of all, thank you to the Mayor and to Westside and for everyone here for coming out to take a look at our presentation, to see what we have to offer. It's quite rare, actually, that we get an opportunity to actually show it to so many people, the people on the internet as well. And so that's great. Thanks very much. I'm Brian Chan. I'm a project engineer, project manager with ECOfluid Systems. We are a Vancouver-based company, and we have responded to the request for technical submission. I'm just going to go through. I'll have an agenda, but before we get past this first slide, I just want to tell you a little bit about what we're looking at here. This is a treatment plant that's being built right now in Chengde in China. It's a treatment plant that we've designed. It is for 15 million liters per day, which is within the scale of what we're talking about here. So what you see in this picture is very similar to what potentially we would be building here. So for this presentation, I'll talk a little bit about our company, our treatment process, our treatment processes. We have a core process. I'll get into that, and then surrounding processes, technologies. Of course, the benefits, certainly the highlights that we like to point out, we can go through. We'll get into the proposal specifically for Westside, and then we can take a look at a few case studies of plants that we've built. So ECOfluid was established in 1995. We, in the past 20 years, have been involved with, designed, built, operated over 150 installations, predominantly in North America and the Caribbean. As I mentioned, the types of service we can offer are quite varied. We can do the process design, we can do process equipment supply, we can do design build, we can do a variety of services to best suit the clientele. In 1998, we completed construction on a treatment plant for a private developer. And at that time, the developer didn't have anyone to operate the treatment plant. So they came to us and they said, would you be able to do this? And we said, yes, absolutely. We have the knowledge and we have the expertise. We can operate that for you. So in 1998, we actually established an operations and maintenance division, which is still running very strong to this day. We're currently operating about half a dozen or so, maybe a few more treatment plants, mainly in British Columbia, but we do also extend our reach, providing some supervisory services in California and Jamaica and different places in North America and the Caribbean. In 2012, we were acquired by a company called NORAM Engineers and Constructors. NORAM is a fairly well-known company who are quite involved with chemical treatment plant or chemical plants, whether it be nitration, sulfuric acid, electrochemical. and they were looking to round out some of their services. They also have a wastewater treatment division, as you'll find out shortly. And they were just looking to round out some of their, what they had to offer. So between ECOfluid and with the help of NORAM, we are able to provide design, engineering expertise, operations expertise. We have business development people who will work with clients, and this team that we've put together is very, very well suited to support a variety of different clients, a variety of different projects. So as I mentioned, ECOfluid is able to provide process and mechanical design for a complete wastewater treatment plant from the very front to the very end. And the types of processes and technologies that we're very well versed in include pretreatment and headworks, into biology or secondary treatment. Again, our specific expertise is with upflow sludge blanket filtration, which is a patented treatment technology. We've also looked into membrane bioreactors and MBBR technologies. From there, we can go into tertiary treatment, which will include polishing filtration, whether that's sand, microscreen, cloth media, membranes again, and then disinfection. That's the liquid side of things, and of course there's the solids to deal with as well, and we can, again, deal with those through various methods of dewatering. The USBF technology, as I mentioned, is a patented technology, but that doesn't mean that it's a secret black box. It's actually it's well-established technologies put together in such a way that there's a lot of benefits that are realized because of the configuration that we put them in. The way that it works is effluent comes into our bioreactor, USBF bioreactor, goes through an anoxic compartment or tank or zone where the wastewater goes through denitrification. From anoxic, it goes into aerobic, where it receives oxygen and is nitrified. And then finally, it goes into the sludge blanket filter. The sludge blanket filter is basically a clarifier that provides an environment by which the wastewater or the mixed liquor forms its own fluidized filter bed. So in other words, it's filtering itself. And the way that, because of the geometry and the way that the SBF is set up, the flow comes in from the bottom, filters everything out. You get clear effluent at the top, which is drawn off. From the bottom of the SBF, we can collect recycled sludge to send back to the anoxic zone, which is used as a carbon source for denitrification. And we also, of course, have a waste sludge stream off of that. So just to take a closer look at the process, again, on the top left, you've got influent wastewater, comes into the bioreactor. There it is mixed with recycled sludge and goes through the anoxic compartment and is denitrified. From the anoxic, it goes into aeration, or the aerobic compartment, where it undergoes nitrification. And finally, the mixed liquor goes into the sludge blanket filter. Again, with an upflow pattern, we get natural settling of the sludge and also formation of a fluidized filter bed. And from the top, we can collect clarified effluent and take it to the next step of treatment if required. Everything is contained within a relatively compact bioreactor. Everything within this process diagram right here is gravity flow. There's no pumping involved. Everything is just flows by gravity. And this is where we get two of our biggest benefits, which are reduced footprint and reduced energy consumption. So again, some of the benefits of USBF are we get a high treatment efficiency. There's a built-in biological nutrient removal, which happens. Again, I mentioned the denitrification and nitrification. The other thing that we get is phosphorus reduction through a process known as luxury uptake. Basically, the phosphorus is stored in the bugs in the sludge, and as the sludge is taken out, we're also taking out phosphorus. The bioreactors are compact, as I mentioned. They're also modular, which means that we can expand at any rate and pretty much ad infinitum, theoretically. This is particularly useful, especially in communities where you're foreseeing growth and you want a long-term solution where you don't necessarily want to spend all of your capital up front because you don't need that much capacity at the beginning. So again, the modular expandability of the technology is, again, inherent, and that's something that appeals to quite a few people. The aeration, extended aeration, results in basically no odor. We don't have odorous bioreactors. We have open air bioreactors pretty much at all of our plants, and we just don't get, a lot of the time, if people don't see it, they don't even know it's there. Same with noise. We don't have a lot of pumping. We don't have a lot of rotating equipment, and therefore we are able to reduce our noise footprint as well. Again, with the gravity flow through the bioreactors, that provides a built-in benefit. The combination of all these things results in reduced capital expenses and also reduced operating expenses, again, with not too much in terms of rotating equipment, the simplicity of the technology. It's all combines to make a more operator-friendly environment. One other thing we get is, again, the filtration. We get filtration inherent in our technology. Fluidized bed filtration is something that's, given the geometry of this system, something that is where it's able to regulate itself, whereby the higher your flow, the bigger your fluidized bed becomes, the bigger your filter becomes. When you have lower flows, things settle back down, the area of your filter gets smaller. So Westside specifically are looking at 3 treatment scenarios. One is the mandated treatment level. mandated by the WSER, which is the federal regulation for wastewater discharge into receiving waters. There's the additional or advanced treatment level 1. Sorry, the mandated treatment level is 2525 BOD and TSS, less than 1.25 uniodized ammonia. Advanced treatment level 1 is 1010 BOD TSS, as well as a disinfection requirement. And then advanced treatment level 2, which basically will allow you to do whatever you want with the water, almost, is down to 5.5 TSS and BOD and stricter disinfection levels. To meet the mandated treatment level, we would be looking at our core technology, which is USBF, sludge blanket filtration. So if you start on the left side there, there's the sewage comes into the plant, goes through an integrated headwork system, which would involve screening. It would then flow into the equalization tank. From there, the sewage would be pumped into the USBF bioreactor. And again, it would go through anoxic, aerobic, and the sludge blanket filter itself to come out at the mandated treatment level of 2525 BOD and TSS and less than 1.25 uniodized ammonia. Solids would be taken off, waste solids would be taken off and dewatered through centrifuge or some other technology and taken off-site. In order to meet one of the advanced treatment levels, or either of the advanced treatment levels, we would really just be looking at adding polishing filtration on and then disinfection. So again, taking the effluent out of the USBF bioreactor, we would send it through either microfilter or for the most strict level of treatment, membranes. And then through UV disinfection and whatever reuse would be planned after that. So again, we're really, we have a very simple technology with a very simple approach. There's not a lot of moving parts, and we can meet these treatment levels fairly easily. Here. Getting into the land requirements part of the request for technical information. There were a variety of different flows or sizes of treatment plant that we were asked to look at and respond to. We really took the lower half of those flows. Again, one of our benefits is we're modular and we're expandable. So up front, we're looking at a situation where you probably don't need 50 megaliters per day. So we looked at 5, 10, 15, and 20. At 5 megaliters per day, we are roughly just over 3,000 square meters in terms of footprint. This is for the entire plant, not just process, but including all of our buildings, roads and parking access, that sort of thing. That works out to about 0.6 roughly square meters per cubic meter of treatment. When you work your way up, or that would be roughly, say, a 60 by 60 meter lot. As you work your way up, at 10 10 million liters per day, we're looking at maybe about an 80 by 80 lot, at 15, 85 by 85, and at 20, we're looking at roughly 100 by 100 meter lot. So 20 million liters per day would be roughly 10,000 square meters, which works out to about 0.5 square meters per cubic meter of treated water. Power consumption, again, we don't utilize a lot of rotating equipment, particularly pumps. We do have the gravity flow, and as such, we find that we have generally a lower power consumption than other technologies. Right across the board, for the mandated level of treatment, we're looking at about 0.4 kilowatt hours per cubic meter treated, and these numbers are backed up by all of the treatment plants that we operate with the exact same technology. In terms of staffing, at the 5 megaliter per day level, for the mandated treatment level, we're looking at 3 full-time operators, a requirement of 3 for your O&M staff. At the advanced level, we would jump up to 4 operators. At 10 megaliters per day, we're looking at 4 for mandated treatment level and 5 for the advanced. 15, we're looking at 4 for mandated treatment, and again 5 for the advanced. And then for 20, we're looking at 5 full-time operators across the board. Capital costs, which is a very important point. I think probably something that just about everyone thinks is the most important thing. We are looking at, again, for the mandated treatment level, in the range of about $10 million for the 5 megaliter per day plant, which works out to about $2,000 per cubic meter of treated water. And working up to about, again at the mandated treatment level, about $23 million for a 20 million liter per day treatment plant. That works out to just over $1,000 per cubic meter treated water. So I'm just going to go through a few case studies, a few different plants that we have built and are operating right now. The first one is in Florida. It's in a city called Lake Alfred. It's a municipal plant. It was retrofitted from a different technology into USBF. It is a 4 million liter per day plant, again in the range of what we would be looking at here for Westside. The top left picture shows the footprint of a USBF bioreactor for 4 million liters per day, or 1 million gallons per day in the US. Again, it's a retrofitted plant, so we just took existing tankage where we could, existing equipment where we could, and put in our own technology. From this, we get, Florida was actually one of the first jurisdictions to really take the bull by the horns and start mandating nutrient removal. And again, just from USBF technology, we're able to get the water down to a water reuse quality with reduced nitrogen and phosphorus. Next plant, the next case study is Strathmore, Alberta. Again, it's a 4 million liter per day plant. In this case, it was a design, supply, and install contract for us. Again, one of the objectives was nutrient removal, specifically in this case phosphorus, and of course it is a cold weather operation which often hinders nutrient removal, nitrogen specifically. So again, that's the footprint that you're looking at on the left side is a footprint for a 4 million liter per day USBF bioreactor. The process, as I mentioned earlier, it does remove phosphorus naturally through luxury uptake. Generally, to get it down to levels, to get phosphorus down to levels of less than 1 milligram per liter or lower, we need a little bit of help. In this case, we use aluminum sulfate to precipitate out the remaining phosphorus into the sludge. So the bottom right picture that you see there is the chemical addition system for the alum. Again, this is a 4 million liter per day plant, and those pumps are about the size of this laptop, if not smaller. It's very, very small dosage of alum to get the remaining phosphorus out. The last case study to be presented is at the Sun Peaks Ski Resort here in BC. This current size of the plant is 1.5 million liters per day. This plant actually started much smaller. I think it was about 0.6 or so, and has grown modularly as the demand has risen and as the resort has expanded. Again, it's a cold water or a cold weather operation. There's a lot of, as with any resort, there's a lot of day flows, day visitors. So the loading characteristics are different and often heavier than what you find with just regular municipal wastewater. And Sun Peaks has been one of our best clients. They're very happy with the system. Again, they've expanded twice since the original installation, and they're up to 1.5 million liters per day. On the top left, you see the original installation. On the top right, that was the latest expansion to add another 300 cubic meters per day. And again, they have headworks on the bottom left and sludge dewatering on the bottom right. So it's a full package plant that we designed for them. Just to give an idea of other things that we do, other size plants that we're capable of designing and installing, and other services that we're able to provide. On the top left, you'll see the Nanoose First Nations wastewater treatment plant just outside of Nanaimo. That treatment plant houses 280 cubic meter per day modules, so 160 cubic meters per day, including polishing filtration through sand filters and UV disinfection. So as you can see, it's basically about the size of a house. And it is, for all intents and purposes, invisible, and there's no noise signature to speak of. It's one of those situations where if you didn't know it was there, you wouldn't know it was there. You'd never notice it. To the right of that is a plant that we just put in almost 2 years ago now in Joshua Basin, California, just outside of Palm Springs. Again, this plant is sitting, the plant is in the foreground, and in the background is a sheriff's station. So, again, one of those situations where noise and odor, not an issue. Bottom left is the Senkulmen wastewater treatment plant, owned and operated by the Osoyoos Indian Band. And it's another installation that was expanded. The first module was put in 2009, and we just finished the expansion a couple of months ago to accommodate federal correction facility amongst other clients who are going to come online for them. I should also mention that Nanoose and Senkulmen, those are both operated by the bands that own them. Nanoose was a plant that, when we built the plant, INAC, the Indian First Nations ministry, they wanted some band members to be trained to operate the plant. So we were very happy to do that. One of our senior operators trained 2 of the band members, and to this day they're still operating the plant. They're both eligible for their level 1 operator tickets, and it's a nice little success story for us. Senkulmen, again, similar situation. We trained some band members to operate the plant. They're still there to this day. They're doing a great job. It's a beautiful plant, and it's operated very well. And finally, on the bottom right is the Mill Springs wastewater treatment plant just up the road, just up Highway 1 here in Mill Bay. At the time that this plant was built, it was in the permit era. It was issued the strictest permit in British Columbia because the discharge is right over an aquifer. So essentially, we were, and still to this day are, doing water reclamation, where we're recharging the aquifer straight from the treatment plant. So that's about all I have. Just to give again, just to give a general overview of who we are and what we do. If there's any questions, myself or Karel, Galland, who's the president of the company, would be happy to answer them. Yeah.
First question is additional. My first question is the additional filtration for the phosphorus and that with the alum thing. Is that only because that was cold weather?
No.
Is that a different?
No, just to go back, there wasn't actually additional filtration. It was just a chemical addition, yeah. That was mandated because that was as specific to that discharge requirement, was the low phosphorus requirement. Generally, in a municipal setting, strictly with USBF technology, we can get down to, let's say, about 3 milligrams per liter of phosphorus in the effluent. If we need to get lower, that's when we need to add in a chemical dosage to polish the phosphorus.
On a lighter note, what filtration did you guys have to implement when you put that federal correction online to keep inmates in?
Well, we haven't gotten into the correction business yet, but yeah. Yeah. Yeah.
You showed one illustration where the facility was enclosed. Is there any technical reason why you couldn't put a permanent cover on top of the facility and then build a high-rise structure or something?
There's no reason at all you could do that. That particular plant, I think you were talking about Nanoose, where it was inside what looked like a house. The only reason why those bioreactors are inside in that case was strictly because of the contract. They wanted them to be completely hidden. Just about every other bioreactor or treatment plant that we've built has open bioreactors. That's not to say that you cannot cover them. Certainly you can cover them, you can build over top of them. There's a couple of facilities right now, one we're doing in California, they're building a parking lot on top. You can, as long as you have access to the treatment plant, there's no reason why you can't enclose it.
Is there any reason you can't bypass the bioreactor and go straight to, say, something like Z-weed filtration?
No, there's no reason.
So we don't really need that bioreactor.
What you're talking about, you would still need a bioreactor. You're talking about membrane filtration.
Correct.
Yeah. Membranes traditionally are immersed into a bioreactor. You still need a bioreactor. You need the biology to get to secondary treatment. All the membranes are doing is filtering out water from sludge. That's all the USBF is doing as well. It's filtering out water from sludge, separating water and sludge. We have an installation on Bowen Island where we have USBF technology with an ocean outfall discharge whereby we're able to take a side stream, run it through membranes and UV, and that water they reuse on site. They use it for processed water. They can use it for irrigation. There's a park, there's a old GVRD park right there. There's a school nearby where they have fields where they could use it for irrigation. They could use it for recharging a stream nearby. They could use it for anything. What we have found is that, imagine if you take a membrane and you have tiny, tiny, tiny pore sizes and you stick it into a really muddy river. Think about the pressure that you have to put on those membranes to get that muddy water through, to get the clean water on the other side. Now stick the same membranes into a clean river. It takes a lot less pressure to strain out that mud. That's essentially what we would be doing in the case of membranes, using membranes as tertiary filtration. You'd still get the same treatment level, but you would work a lot less hard to reach that treatment level.
Now, in terms of your dewatering, that's a third party you would go to dewater the sludge?
Yeah, likely that would be a third party,
Yeah.
that's right. Yeah.
And then the same with gasification, that would be a third party.
That's right, depending on what option is chosen for dealing with the solids, whether it's done on-site or not on-site, all of those things are a little bit up in the air. Generally, our core treatment technology is sludge blanket filtration. That's how we can take water from being raw sewage to getting it to secondary levels of treatment. Everything else in terms of dewatering, composting, whatever you want to do with the solids, everyone's in the same boat. Everyone's going to go find a Purelisi or whoever, some centrifuge manufacturer, and they're going to work with them, and they're going to find what they think is the optimal solution.
Do you have any idea what size of staging area you would need to, say, mix sludge and wood chips or whatever else you were going to put through a gasifier? Do you have any information on that?
Well, no, I don't have any information right now. It's very dependent on the size of your treatment plant. It's dependent on whatever the technology is that you decide to, or whichever vendor you decide to go with. So I don't have any information right now.
I had a question on shutting it down for maintenance.
Mhm.
Is it designed in trains, individual trains?
Yep.
So the one plant would have, like say a 5,000, how many trains would that actually have?
So,
Individual?
okay, so for the you're talking about
Or
5,000 tons.
five
Yeah,
million.
5,000 cubic meters per day.
Yes.
That, let's go back here. So again, Lake Alfred is a 4,000 cubic meter a day facility. 5,000 would essentially look like that,
Okay.
at the top left there.
Mhm.
And what you're looking at is 4 different cells, each cell having 2 sludge blanket filters inside of it.
And so
You could shut down any one of those and run the other 3 at any time. They can operate completely independently of each other.
yeah. So on an annual basis, you would probably take each one down in series, depending on, I guess,
Yeah, yeah.
the level of, and for fat oils and grease, how is that treated?
Well, I think you're going to, again, find this situation with just about everyone. Fat oils and grease, we can deal with a certain amount. Once you exceed that amount, you'll get things like foaming and things like that. These are generally, it's not detrimental to the process necessarily, but it's not something that you desire in the process. So what you try to do is take out fat oil and grease on the front end. Again, in your headworks or through some other technology like dissolved air flotation or whatever it is, you would try and take it out before you get to the biology.
So that would be incorporated in your design then?
That's right, yeah.
And the headworks, so does your process require a certain level of screening? Like, I know like the xenon units, you have to have like 2 to 4 millimeter screens or else their processes
Yeah.
are similar or?
No, I would say that 4 would be generous even for membrane bioreactors. They really
Yes.
try and take everything out before it even gets to the bioreactor. In our situation, we have gone, the finest we generally go in terms of headwork screening is about 6 millimeters, a quarter inch. We don't have to go that fine. We can go, say, half an inch or 12 millimeters. Or maybe, again, depending on the size and the scale of the plant, the size of the pump intakes, things like that, we could go larger than that even, 3/4 or an inch or whatever. To answer your question in a more of a general sense, yes, we require screening. No, we do not require fine screening, really fine screening.
And grit removal?
Yeah, we would have grit removal in our
Because that would be
that would be part of it.
detrimental to your,
Yeah.
that adds a lot of maintenance issues if you don't
That's
have
right,
proper
yeah.
grit removal.
The less sand you run through your pumps, the better you're going to be. So,
Okay.
yeah.
You've talked a lot about the modular nature of the facility and that. In this particular situation in the Victoria general area, is there any such thing as one big plant is more economical than 4 small plants? Or?
Well, I think
I know there's land and there's all kinds
Yeah.
of other issues, but from your plant point of view, is there any benefit in a bigger plant versus multiple small ones?
I don't know if I'm able to answer the question from the CRD's point of view. I know that they've spent a long time examining that specific issue and have, looked at the pros and cons of both situations. For me personally, I believe that smaller plants are better. The reason why is because when you have a catchment area that your sewage system treats, collects all the sewage from X catchment area, why would you want to take all of that and pump it way over there to some other jurisdiction, to some other plant, when you could just treat it within your catchment area? Next door to you, you'll have another catchment area, and you could have another treatment plant. There doesn't have to be a situation where you take everyone's sewage and just pump it to one plant. There are situations where, yeah, that works. But the more spread out you become in terms of geography, the more relief you get in terms of hills and valleys, all these things play into it. And again, my personal thought is that in general, you're often better off to treat as locally as possible. The other thing is you save your water back into a local system. Now again, depending on your geography, that might not actually matter. But in a general sense, that's what I would say.
One last question. When you've got a demand that includes stormwater and you get into peak loadings, is there any requirement for regulating the flow, the input flow? Do you need like surge tanks or anything of that nature?
Yeah, absolutely. So in our configuration, and probably in everyone's configuration, we'd be looking at some sort of flow equalization. Generally what we do is, again, we have everything runs through a headworks into an equalization tank. From there, we're able to regulate what flow we push through the plant at any given time. So we want to take out those peaks and valleys. We want to even things out, and that's the purpose of the equalization tank.
I'm assuming your cells are stackable, apart from the pumping costs.
In theory, they're stackable, I suppose, yeah. I think that if you were to go that route, you would find more challenges than it's worth. Structurally, for example, particularly being on the West Coast as we are, earthquakes are always a concern. I think the last thing you'd want is a ruptured tank in that situation. But in theory, yes, they're stackable.
I want to thank Brian from ECOfluid for his presentation. If anybody has any more questions, you can go online and email info@westsidesolutions.ca, and we can get those questions to the folks at ECOfluid.
Anybody in the room have any further questions before we?
I was wondering questions like, can you remove superbugs, chemicals, pharmaceuticals? Can you drink the water coming out of the system of your tertiary treatment?
In theory, you could probably drink the water, yeah. I'm sure you would live, yeah. You'd probably have psychologically, you might have some, issues, but the thing about, super bugs and all this stuff is these are sort of the buzzwords that we have today. A lot of these issues can be solved through either disinfection practices or your level of tertiary filtration. These things are not the horrible disasters that some people hope to make them out to be. So yes, You could drink the water on the other side, absolutely. Yeah, with the membrane filtration and UV disinfection and all that stuff. Yeah.
Water sewage would you remove per day from your facility?
Of water?
Oh, no, sludge,
Oh, of sludge.
Dewater.
Well, it depends on the size of the plant. Generally, and this is again going to be true for just about everyone, generally, centrifuge, for example, you can dewater to 20% dry solids content. So if you start with, say, I don't even know, 0.5% in your mixed liquor, then you're reducing, you're taking out almost all of the water. Not almost all, you're taking out quite a bit of the water. So, again, it depends on the size of the facility, it depends on what you're able to haul, it depends on bin size, it depends on configuration of, but probably for a plant this size, you wouldn't be looking at more than one or maybe 2 truckloads a week, something like that, just as a very rough guess.
Would you put your biosolids on the land, or would you take them to landfill and let them deal with it?
That is completely up to Westside. That whatever solution they come up with is the solution that we would design for. Again, that would depend on land availability. It would depend on permitting, viability of being able to sell biosolids or compost, or even being able to give it away. You look at a jurisdiction like GVRD, they produce a lot of biosolids. There's 1.8 million people in Greater Vancouver, and that produces a lot of biosolids. They can't even give it away, So there are lots of things that Westside and CRD will have to consider.
Anybody else? Final question? There we go.
You mentioned that the effluent could be drinkable. Is that allowed through
No,
health
it's-
requirements?
No, it's not allowed. No.
If I may.
Yeah.
It's actually done already. There is I think it's in Orange County in California, where they have a system going, and it's totally drinkable. And in fact, what I read and what I see is that the water is actually better in terms of the natural water. But because of yuck factor, they still put it into the aquifer. But there is a difference between discharging to aquifer like we do in Mill Bay, where we discharge on the ground and then it seeps into the aquifer. There in California, they inject aquifers directly now. So it is possible. By the way, it's not, it's much more than what we are showing here would be required to get to that stage.
Is there anything proprietary in your equipment or design? Could it be tendered publicly, or is it a proprietary type of system?
The USBF bioreactor is a proprietary system. That is our design, and that is a patented design. As I mentioned previously, there's nothing specifically mysterious or new about it. It's just the way that the bioreactor itself is configured. The operation of the USBF is very, very simple. It's very easy to train people to do it. Again, the processes that are going inside there are nothing new. People are very familiar with the biology itself. But again, as far as the USBF technology, yes, that's proprietary. Everything else is quote unquote open source.
Now, of any of the proprietary stuff, that what kind of design life do they have? You know, you're talking replacement every 5 years, 10 years, 50 years? Or?
Replacement as long as the concrete lasts. There's nothing inside there that's, you know, there will be things that require maintenance. There will be things that break down over time, over 5 years or 10 years, you know. Pumps generally don't last more than, let's say, 10 years. Not that we have pumps inside, but in a general sense, you know, mechanical items have a lifespan. The treatment technology, the technology itself is actually, it's quite old in the sense that this company was established in 1995, but the technology itself came from Europe before that, and it has been operating around the world for decades, and it continues to work. It's very simple. It's very simple. It will last as long as that concrete tank lasts.
And as far as the potable nature of the effluent, I guess the International Space Station, they have solved that, I guess.
Yeah, I'm not sure what they do. I'm sure there's reverse osmosis involved. I'm not too sure. We haven't gotten that far yet.
Anything further? I think that comes to an end. Thank you very much.
No, thank you. Thank you.